videos for all of these things I'm going to do today that will walk you through. They're silent videos, so I'm not explaining. It's just kind of watching. I'm going over the construction. So you can pause the video and follow along, and that's linked right here at this link. So that's kind of my my goal for the day. I have 6 things. Most of these are for high school, 9, 10, 11, and 12. And I tried to kind of get some things that were a mixture of geometry and algebra. And so the first thing I want to start with is is a dynamic parabola. And so this is a cool thing. Now I prefer in GeoGebra, I prefer classic. That's just me. That's the one I prefer to use. I'm comfortable with it. I kind of know where everything is. Everything I'm doing in classic should work in the other apps over here. But I'm going to use GeoGebra Classic. So I'm going to click on Classic over here. And I don't know why. Why do all these windows open up? All these weird windows. Let me close these windows and let me go to the pancake stack in the upper right-hand corner and let me change my perspectives. I tried it. It's weird. I never know what I'm going to get when I open this up. And I'm going to go to graphing. And so I just got the plain old graphing. So here's what I'd like to do. I want to make a parabola that is really flexible and really dynamic. And at the same time, I'll try to point out some kind of cool little GeoGebra things that you can do. So what I'd like is I'm going to use the point tool. And I want point A can be my vertex, and point B will be another point that the parabola goes through. So in other words, I'm thinking what's going to happen is my parabola is going to look something like this when I'm done. Oh. That says an ellipse, but I'm going to undo that. I did not expect that to happen. So what I'd like to do is I want to have again, that's going to be my vertex, and point B is going to be another point. And so this is really cool. This is kind of a thing that most folks don't realize, but I'm going to go ahead and type in f of x as my start, and maybe I can zoom in here to see, you guys can see a little bit better. And I'm going to make a fraction because I'm going to have to scale my I need to scale my parabola so to make it fit my 2 points. And so in this scale, the numerator is the y coordinate of B minus the y coordinate of A. So that's kind of like is the vertical change between the vertex and that other point. And then in my denominator, I'm going to place in parentheses, I'm going to place the x coordinate of B minus the x coordinate of A. But what I'm going to do is I'm going to square that denominator. And so this is actually going to be the scale for my parabola. And then I'm just going to do my translation, x minus the x coordinate of A squared plus the y coordinate of A squared. And so this is a general form for a parabola. So really, if you think about this, in the United States, we always refer to slope as rise over run. I don't know if you refer to it that way. And I can't see the chat to even respond to anybody. So, oh well, that's the way it is. But this is, instead of rise over run, which is what you would get in a linear equation, this is the rise over the run squared, which is what makes sense for a parabola. So let's scroll out and let's see how this looks. So this is a super flexible, super dynamic parabola. And so what I can do is I think it'd be cool. I'm going to try this. Let's see what happens. I want to lock the points at the integer coordinates. So in the upper right corner of my graphing page, I'm going to click on that little menu, and well, I better click in the space first. So I'm on the graph, and then I can set the point capture style, and I want it to be fixed to the grid. And so now when I drag these points, the points will now stick to the grid. And my equation here, my equation on the left side doesn't look really pretty. So I'm going to do, what I'm going to do is I'm going to use a simplify command. And I'm going to simplify function f. And so now I get a little kind of better looking, kind of a function. And so actually this is like 2/9 times this quadratic. And 2/9 comes from this. So again, 2/9. That is 2. And this is, man, my drawing is terrible. Oh my goodness gracious. That's 3. And so you remember we did rise over run squared. So 2 over 3 squared is where the 9 comes from. So let me see if I can select that and delete that stuff. That is perfect. So if I drag this down like that, that is going to be 1/9. And I'm here. What happens if we go here? Now it's a perfect square. And if I drag it up like that, now we have, see my factors. I have x plus 1, and I have x plus 5, and I have a negative 1/2. So that's a dynamic parabola. A dynamic parabola that is super flexible, and something that when I used to teach my algebra classes a few years back, I'd walk my kids through this. I wanted them to create things in GeoGebra that were super flexible, that I could drag them anyway, and they would always stay the way they were. So that is the first thing. That's the dynamic parabola, and there is a video of that. And hopefully I will get those notes to you again, the link to that, because I don't know where my chat window goes. So let me go to the next thing. The next thing on my list, is the cubic curiosity. There are 2 of them. So a cubic function, and most folks, like even my calculus teacher friends that I know, have not seen the first cubic curiosity that I will show you. But this is really, I think this is kind of cool. So I'm going to go back and go to my GeoGebra Classic again. And I don't know why it does this. I don't know why all these other windows. I must have saved something. I must have saved something kind of weird. So what I'm going to do is I want to make a I want to make the equation of a cubic function that is based on the roots. And so, for example, I'm going to use the point tool, and I want one root to go here, one root to go there, and another root to go there. So I want a cubic function that will pass through those 3 points. And I'm going to build it the old-fashioned way. I'm not going to use regression or anything like that. I'm just going to go, so I'm going to go x minus the x coordinate of A times x minus the x coordinate of B. There's our parabola. And then times x minus the x coordinate of C. And so that gives me a very flexible cubic equation that is controlled by the roots. As I drag the roots back and forth, this is how I can change the equation. This is a little trick kind of right here with the x of A. That's something that most folks don't know, but this is one of the things that drew me to GeoGebra about 12 or 13 years ago. I started playing with GeoGebra back in 2007. And this was one of the things that I never could do easily in Geometry Sketchpad, and that's to use the coordinates of points in a calculation or in some sort of equation. That was always trouble for me. So here's the cubic curiosity. What I'm going to do first is I'm going to construct the midpoint of A and B. So I'm going to go up here to my point tools, and I'm going to select the midpoint, and I'm going to go from A to B. That's the midpoint. And so what I'm interested in is I want to create the point on this function that's directly above point D. I could do this algebraically, but I could also demonstrate some of the geometry tools. So if it's directly above point D, that's essentially a perpendicular line through point D, and I'll find out where it intersects that function. So I activated the perpendicular line tool. I will click on the axis, and I will click on point D. And so what I really want is I want that intersection point right there where the function and the perpendicular line cross. So I'm going to select my intersect tool, and then I'm going to click on my function, and then click on the line, and there is my there's my point. So again, in summary, what I've done is I've created a cubic function that is super flexible, and then I created a point on that function that is essentially halfway between two of the roots. So E is halfway between A and B, no matter where I drag A and B. Now this is cool. This is cool. And this is the thing that most calculus teachers that I know, my friends here, haven't seen. But this is something that a calculus teacher, their students should be able to prove this. So what I'm going to do is I'm going to create a tangent line to this function at this point E at the top. And there is a tool for that. So underneath my construction tools, about halfway down, is a tangent tool. So I'm going to activate the tangent tool. Click on the function, because I want to be tangent to the function, and I want to go through point E. And oh my goodness gracious, I have got to find my chat. Where the heck is my chat? I don't know where it goes. I want to see what you guys, I'd love to see. I don't know where the chat is. It must be behind. It must be behind all of my stuff. That's the only thing I can think of. Oh, I found the chat. I found the chat, kids. Okay, now everything is better. So this is a, so what, in the chat window, what do you notice about this? What do you notice about what's happening here? What is the curiosity? I made a midpoint between two roots and I constructed the tangent. What do you notice about this? Oh, what happened? What does that tangent do? What do you notice about that tangent? Oh man, when I drag the roots around, it goes through the, yeah, it goes through the other x-intercept. Have you guys seen that before? Our calculus teachers here in the United States typically don't see this. And this is something that calculus kids should see. This is something that calculus kids should see, and they can easily prove this. They can easily prove this. Yeah, so, and it doesn't matter where my roots are located. It always goes through that third root. So that's my first cubic curiosity. That's my first cubic curiosity. Okay, now that I find the chat, everything's cool. Okay, so here's my second one. Here's my second cubic curiosity. I'm going to go up here. This one has more of a geometry flavor to this. This has more of a geometry flavor to this. I'm going to create a new, I don't want to save this. Perfect, perfect. So this is a, yeah, I think there's some cool things. Well, I agree, there's some cool things on this. So here's what I'm going to do. Here's what I'm going to do. I'm going to construct an equilateral triangle just up here somewhere. And so there's a tool that does that. So there's a regular polygon tool. And so this is there's a little geometry flavor to this. So I'm going to click here, I'm going to click here, and I want there to be 3 sides. And so this is pretty flexible. This is pretty flexible. And so I can move this around. And what I'm interested in is, here's what I'm interested in, is I want to know, I'm going to drop perpendiculars to the x-axis from this triangle. So I'm going to go A, perpendicular there, point C perpendicular there, and point B perpendicular there. This is an awesome connection between geometry and a cubic function again. And so what I'm going to do is I want to construct the intersection points of the roots here. So, and I'm going to use those intersection points to build a cubic function. So I'm going to put a point here. So let's see. Oh, better not do it that way. I better use the intersection point. I better be proper. Let me go. I want to intersect this line and the axis, this line and the axis, this line and the axis. And so just like I did before, I want to build a cubic function that passes through D, E, and F. So I will go x minus x coordinate of D times x minus the x coordinate of E times x minus the x coordinate of F. And so now when I drag my equilateral triangle around, my cubic function also changes. Now, so a little more geometry. What I want to do is I want to construct the inscribed circle for that polygon. Luckily for me, there is a command that says encircle. So there's actually an encircle command that takes the 3 points of my triangle. So if I go encircle ABC, it will construct the inscribed circle for this. So, I was afraid this was going to come up. Can we integrate graphs and geometry created in GeoGebra into our Desmos activities? So, if you want to, first off, I'm glad you want you're using the Desmos activities. If you want to put a GeoGebra thing into it, you've got to link to it outside. You can't put it directly into a Desmos activity. That said, ready? GeoGebra is coming out with a version of an activity builder where you'll be able to track student progress in real time as they work on GeoGebra activities. And you can see more about it if you went to beta.geogebra.org. There's a beta website that you can go to and see this, and it's called Classroom. And you can start messing with it. You know, they haven't announced it yet because it's still got a couple things they're trying to finish up, but they're supposed to roll this out before the beginning of next year, by the beginning of the next school year. But I do agree that the graphing tools in GeoGebra are much more powerful. So let me get back to this. So I've got my circles. I want to construct the center of the circle. And to do the center of the circle, I'm going to use the midpoint or center tool, and I'm going to activate this. And so that's the center. That's the center essentially of the incircle, but also the centroid because it's an equilateral triangle. And I'm going to drop another perpendicular from that point to the x-axis. And so calculus teacher friends, if you are a calculus teacher, or if you teach about these things, that point where that perpendicular crosses the cubic function, is there anything special about that point? Do you think there is anything special about that point right there? And one more thing. Oh, let me cancel this. What I want to do is I want to construct tangents to this circle that are perpendicular to the x-axis. And it is the inflection point. That's correct. So what I'm going to do is I'm going to construct a parallel line to the x-axis. Oh, I'm not going to do it that way. I got to hit the x-axis if I'm going to construct it. So x-axis through the center. And then I'm going to construct the intersection points of that line. Nope, not that. I'm having some clicking issues. Okay, ready. I'm going to go intersection point, this line, and that circle. And then I will construct perpendiculars from those points. So look at this, kids. Look at this. This is absolutely, when I first saw this, I was stunned. I was absolutely stunned. Yes. So here is a connection between an equilateral triangle, the inscribed circle, and the center of that equilateral triangle. If the equilateral triangle, the vertices are the roots of my cubic equation, then the width of my inscribed circle actually is the distances between the turning points of my function. And then the center of that circle gives us the inflection points. So I can show that. If I go to inflection, there is a command that does that. And my polynomial, I believe, is, I think it is, it's not F. I think my polynomial's name is P. Oh, I missed. So my polynomial's name is P, so that's the inflection point. And if I go extremum, the extremum is my roots, or my max and min, and my extremum is also those 2 points there. So another curiosity, another cubic curiosity, a connection though to an equilateral triangle and an inscribed circle, and tangents and perpendiculars just dropped from that construction. I thought when I saw this, I was absolutely stunned, absolutely stunned. And there are some wonderful connections with other regular polygons and other functions that you can also explore. But there is there's a video that I will walk you through that instruction that I linked in the that I linked for you in that document. And I think I should probably paste that document here. Oh. And there is a link that should be a link to my agenda item that I placed. So let's go to the next thing. The next thing is, this is going to be more for calculus teachers. So I'm not sure how many calculus teachers. Oh no, this is freehand function. Oh my goodness gracious. Freehand function. Okay. Who in the chat, who has to teach function transformations? Because yeah, okay, me. Yeah, it's all okay. So this is super powerful, guys. This is super powerful, super powerful. I'm going to again, I'm going to go ahead and click up here again, and I'm going to click on new, and we're going to see what happens. I don't want to save this, and it's going to open. Oh, good, it worked. Okay. This is, and even if you do it a little bit, this is going to be fantastic. I think this is one of those things that is just, when you see this and you're going to think, I need to use this next year. So there is a freehand function tool. So if I go up here to my arrow, and I click on that arrow, there is a freehand shape. And so I'm going to activate that. And it shows up as a function. It shows up as f of x. So believe it or not, I can actually do things like this. Like I can evaluate that function at f of -4. So at -4, the function value is 3. So I could, I mean, if I wanted to, I could actually graph that point. I could go -4, comma, f of -4. And I could actually place that point right there on the function. So, and I can drag that point. I mean, this is I can't drag it because that is now at -4, but I can change that number. But if I place a point on it, I can drag this point along the function. So it's like a little chunk. It's like a little piece of the function that that you drew freehand. And so let's try this. Oh, this is I think this is cool. So watch this. This is again, I think this is awesome. So I'm going to go, let's f of, let's translate this to the right 5 units. X minus 5. Or instead of x minus 5, let's go f minus n and see if it creates a function. I probably need to create the slider first. And so what if I can use my, yeah, it might not like that. Oh yeah, it works. So I could actually use a slider teaching my freehand function transformations. And what would we do to reflect this over? Again, we're always referring back to our original function f. So I could go negative f of x. And that places the function, that reflects the function over the x-axis. If I go f of negative x, that reflects my function over the y-axis. I wish I could drag it. I wish I could drag that. And then I can explore what happens when I scale the function. So what if I go 3 times f of x? Whoa, that is way off the screen. So that really stretches it vertically. Or what if I did f of 3 times x? And so that really compresses it horizontally. So I think this is a fantastic way to illustrate function transformations with just a freehand shape. With just a freehand shape. And so then when GeoGebra Classroom is released, again, you can go to the beta.geogebra.org site and play with it. When the classroom is released, this is going to be a game changer because now I can actually see my students manipulate these things in real time. Let me try this. I don't know. I've never tried this before. I'm going to try something that, what if I did a freehand shape? This might not like this. Yeah, because it wants to make a function. It will not allow you to kind of, I wonder what's going to happen here. Let's see what happened. So it actually showed up as an ellipse. So I probably couldn't treat it as a freehand function on this one. So that's something that's a little bit different. So that's the freehand function tool. Very, very cool. Very, very cool. And if you've not seen that, that would be a fantastic way to show transformations of functions and to explore functions and their graphs. And again, I could put points on it and I could apply everything to those points if I had to. So I could place a point and then I could predict where would that point end up on these other reflected images. So, I agree. I think it does apply to grade 8, especially when you're just like reflecting over the axes or even like translating it. Scaling might not, but I don't know. We do reflecting over the axes, and we do translating, up or down, left or right. And so this is when Classroom comes out, when the new GeoGebra Classroom comes out, it's going to be awesome. It'll be really good. So let's see where we are. Let's see where we are. Ooh, ooh, hold on. Inverse functions. Okay, let's see. I wonder. I don't know if there's a command. Let's see what happens. Is there a command? There's inverses there and there's invert. Let's try that and see what it does. It probably did not like that, did it? Yeah, it didn't do anything. It undefined. So but you could certainly do that. You could certainly do that. So in the chat we do scaling of geometric figures. So this is all, and exactly, I think that would work out. I wonder if we could do, instead of using the function tool, oh my gosh, yeah. If I could draw a shape like this, I just don't know what's going to happen if I draw a shape like this. Let's see. So that shows up as a stroke. That's the command. And I'm wondering if I can, for example, maybe, can I rotate the stroke? I don't know if it'll let me rotate stroke 1 by, say, 45. It did. I could rotate it 45 degrees around the origin, so I could actually draw a freehand shape and rotate it around the origin using the rotation command. Guys, this needs to be probably a 4-hour session, because there is so much stuff we can do with GeoGebra. I love Desmos. I love Desmos, but man, GeoGebra can do some cool things. And when the new classroom feature comes out, it's going to be totally different. Totally different. Okay, are there any calculus teachers in the chat? Yes, no. Any calculus teachers with us today? Or is calculus something that you guys teach here? Okay, there are. Okay, cool. Well, so I want to stick with 2D things. I'm going to stick with 2D things. And then we can come back if there's time to talk about these other things more. And so again, one of my, I think, absolutely the coolest thing of all, again, I'm going to open up a new, I don't want to save that. And so I'm just going to make I'm going to make a graph. I think Riemann sums is a super easy to do at GeoGebra. So I'm just going to make a very simple f of x equals, and I'm going to make it just a sine function that has been, oh, maybe I'll make it a sine function if I can type it in correctly. That is maybe moved up 2 units. And so what I'm interested in is different approximations for the area under the curve. And so what I'd like to do is I'd like to maybe estimate the area from A, which is on the x-axis, to point B. And then I need to make a slider for the number of rectangles or subdivisions. I really should be. So slider, and I want my slider to go from 1 to, say, 50. And I want it to go by ones. So that's the command I use to make my sliders quickly instead of going through the tool. My slider will go from 1 to 50 in increments of 1. And so I know what I could do right away. If I wanted to, there is a command for the integral. And so the integral, my function is f, and I want to go from the x-coordinate of A to the x-coordinate of B. And so this does compute my integral, and that number is my integral, the value of it. And if B happens to be to the left of A, that area does turn out to be negative. So really what I'm interested in is how do these various approximations of these other Riemann sums that we can create, how well do they approximate the actual true area between those 2 points underneath the curve? And so I'm going to hide my integral by clicking on the little radio button next to it. And so my first Riemann sum is the lower sum. So lower sum, and my function is f, and it goes from x of A to x of B, and I want to use n rectangles. So the lower sum, every rectangle is, I don't want to say it's below the curve because that's not necessarily true, but the height of the rectangle is determined by the smallest function value on the interval. So this rectangle here is determined by that point, which is the lowest or the smallest function value on the interval, where this one is a right-handed one because its lowest function value is on the right-hand side. But notice how these two numbers compare. as I increase the number of rectangles, my lower sum increases the true integral value from below. From below. And if I drag my b to the left of a, it shows up as a negative value, which is what I would expect to have when I'm doing areas under curves. So that is the lower sum. Likewise, again, let me move my slider back down. This dynamic illustration, in my mind, is very powerful for calculus. I know kids probably talk about it. It's probably trying to draw a freehand. But this is a command. When I taught calculus, my kids could do this command. So this is not a big deal for kids. So likewise, there is another command. If there's a lower sum, there's probably an upper sum. And there is. And it's the function. I want to go from the x-coordinate of A to the x-coordinate of B. And I want to use n. And so likewise, what you'll notice is happening is the upper sum is greater, is kind of above the function value, and the lower sum is below. So my integral is probably always going to be between these two numbers. So as I increase the number of rectangles, the lower sum and upper sum kind of squeezes the integral. So I know the true value of the area is probably somewhere in between those two values, because these rectangles are always kind of greater than the area, and the lower sum is always below the area. Now there are two other commands that I will show you. There are two other Riemann sum commands. One of them is a trapezoidal sum, and again it goes from the function value x of a to x of b, and then n is the number of trapezoids. And I did not. I will click enter, but then I'm going to hide this. And so now, oh, I hid the wrong one. Now we can have that discussion with the kids. Why does this provide you a better estimate of the area than the upper sum or the lower sum does? So as I increase the number of rectangles, man, these two agree. My trapezoidal sum and my integral agree to 3 decimal places now. And if I go all the way out here, probably to 50, I bet they agree at almost every decimal place, except for that last one. And just the area, the area difference, my error factor is just much, much smaller. So again, that's a trapezoidal sum. Super hard to visualize, but it's a fun thing to do. And then the last one is there is a rectangle sum. And the rectangle sum works the way the other ones do. Rectangle sum, function value, x of a, x of b, n, but now it takes an additional number. And if I put 0.5 in there, that's a midpoint rectangle. So every rectangle, the height of the rectangle is decided by the midpoint of the subdivision. Now, what kids don't realize is the trapezoidal sum and the rectangle sum very close to each other, very, very close to each other. And if I change the 0.5 maybe to or I change it to 1 instead of 0.5, then that gives me a right-hand rectangle where every rectangle, the height of every rectangle is determined by the right side of the interval. And if I made that a 0 instead of a 1, if I made that a 0, that would be on the left side of the interval. So now all of my rectangles are always built on the left side of the interval. And so I don't know if the calculus teachers, if you've seen that before or if you've used GeoGebra to do that before. I used to do these things all the time. I had a geometry class of kids that were on the path to take calculus. So I would do things like that in my geometry class before they ever got to this in calculus. So by the time they got to it, they understood this pretty well. So I do think this is something that could be done in a geometry class, just about doing areas under curves to estimate those things. Okay, and this is working out perfectly. So I think we've gotten, there's one more thing left. So we've done dynamic parabolas, the two cubic curiosities, freehand function transformations, and Riemann sums. My favorite transformation. So I'm going to do my favorite transformation with you. This is absolutely, without a doubt, my favorite transformation. So I'm going to create a new function. So this is for the geometry teachers, man. If you're a geometry teacher, this is for you. You've sat through all this algebra stuff. All right, I'm going to click on don't save that. And I'm gonna set I will use geometry. We'll see how this goes. This is my favorite transformation. So when I do geometry and I do transformations, I like to use the letter F. So what do I mean by that? I like to use a letter like this, or a polygon that is shaped like a letter F. What I find with the students can easily pick up on the orientation of the object. So if you're teaching transformations, one of the things I would get my kids to do is I wanted them to kind of look at the orientation. Has the orientation been reversed? Then it's a reflection of some sort. Is the orientation preserved? Is it the same? Then it's a translation or a rotation. So the letter F allows students to see that and pick up on that easier. And so what I'm going to do next is now I'm going to draw a circle. I'm going to draw a circle over here. So there's my circle. And this is my and I don't know if you guys have done this transformation before. This is absolutely my favorite one. And I think it's a transformation that high school kids should see, because all the other transformations come from this. But if I go to the transformation tools up here in the top, let me go to my transformation tools. Halfway down is something called reflect about a circle. And so I'm going to click on reflect about a circle, and I'm going to click on my F, my point F. And then I'm going to click on the circle. Ta-da. This is absolutely my favorite transformation. What is going on here? What on earth is, oh my gosh, it's like I've turned the F inside out. What on earth is going on here? In the chat, have you guys done this transformation before? If you're a geometry teacher, have you done this? Or even if you're not, have you ever seen this, or have you done this before, this transformation reflecting in a circle? So this is not a big deal. Let me show you the mathematics behind this. The mathematics behind this is very straightforward. So what I'm going to do is I'm going to draw, first off, I'm going to reflect a point. So let me reflect in the circle, let me reflect point C in this circle. And I'll put that tool away when I'm done. So notice, like point C, that's, ooh, whoa, so it looks to me like, it looks to, oh my gosh, I just closed the chat. There it is. So this, yeah, so this is a, the mathematics behind this is super easy to do. Super easy to do. It's actually based on golden ratios, or not golden ratios, geometric means. Geometric means. So what I'm going to do is I'm going to construct a segment from the center of the circle to C prime. And then what I want to do is I want to show its I actually want to show its length. So I want to show the label of that point, but I actually want the number to show. Actually, I'll show both, number and name, because that's L. And then I'm going to do the same thing over here. I'm going to keep that window open. I'm going to draw a segment from the center of the circle to point C. And likewise, I want to go ahead, I want to make sure I show that I show its numbers. So I want to show the label, I want to show both the name and the value. And I want to do one more segment. I want to do one more segment. I want to capture the radius of the circle. And again, I want to do the same thing. So I want to go ahead and capture the length. I want to see both the name of that segment and the value of the segment. So the radius of my circle, is about 3.5, a little bit more than that. And let me see if I can kind of make my radius. I want it to get close to 3. That's pretty close. And now I have a 6 and a 1.5. And so I'm wondering, I think the product of these two numbers is equal to whatever the radius is squared. So let's try this. Let's try this. So what I want to do is I'm going to open up my algebra view for a moment. Actually, I wonder if I can just do yeah, I need to show my algebra view so you can actually see what's happening. And so what I'm going to do is I'm going to compute the product of M and L. So M times L is, and that probably popped way back up here to the top somewhere where my numbers are. So M times L is 9.0836. And then I'm going to go N squared. So N squared is also 9.0836. So the general rule, oh my gosh, I'm going to try to write with my pen. The general rule looks like this. I wonder if I can do it with my touch screen. It is M times L equals N squared. So that's a geometric mean. And you see this all the time when you do right triangles. That's a big unit, like that's a big part of our right triangle unit in geometry in the United States is what are all the geometric mean relationships in a right triangle? Well, here's a geometric mean relationship and a transformation that's in GeoGebra and nobody does it. And it's so cool. And there is so much cool art things that you can do. So much cool stuff. Watch this. Let me show you. Let me show you. Let me delete that stuff there. I'll delete that stuff there. Here's what do I mean by cool stuff? Here's what I mean by cool stuff. Let me, oh my gosh, I need to delete all my points. I think what I'll do is I'll hide them instead. No, I'll just leave those points there. I will delete those points. I will delete this. I think what is cool is I'm going to take a line. Let me go ahead and hide my algebra view. And let me right click on those points. And I wonder if I can delete those points. I can, good. And I'm just going to draw a line. I'm going to draw a line segment. And I'm going to reflect this line. I'm going to reflect this line in my circle. So I'm going to click on the line and click on the circle. Oh my. So the reflection of a line in a circle is a circle. Oh my, there is so much cool math that kids could do. I wonder what if I reflect that circle in that circle. Uh-oh. If I reflect that in this. Uh-oh. Oh man. So lines and circles are kind of treated the same. I know. Okay, so let's see. Where am I? I think that's the last thing. So let me post some links for you guys. So I've done these 6 things. I did the dynamic parabola, the 2 cubic curiosities, a freehand function, a Riemann sum, and my favorite transformations. I included a link to my Proof Without Words book. I was trying to think of something for maybe middle school teachers who have to do the Pythagorean theorem. And so this is a GeoGebra book with a whole bunch of different proofs, dynamic proofs of the Pythagorean theorem. So when you drag sliders around, things move around. And some of them are more like puzzles. So, and I think there's a slider down here. So getting kids to try to explain why these different things actually lead to proofs of the Pythagorean theorem. So some are, I'm not a big fan of this one. It's kind of hard to see it, but that worked out well. So a number of different proofs. I think there was over 40. And there are some that are not, this is kind of cool. I like this one. So those are yours that you can play with as well. So let me put this link again in the chat window for you guys so you can see this. I see some of you are in here already, and I do appreciate that. So I'll put this link down there again. There is also, I will show you the results of this link as well. So this link is all the way down here at the bottom. In this, I've created this Google slide, and you can view this. You can view the Google slide, and I've created short little silent videos for all of the things I've done today. And also these videos are reasonably short, maybe 4 minutes long tops, just like we did today. They walk you through, there's no audio, so I'm not speaking, it's just kind of going through the process. And so you have access to that as well. And then in 2 weeks, I think is when we're doing this again. I think in 2 weeks, we'll focus on the 3D geometry types of things. But I'm gonna stop sharing. And if there are any questions in the chat, I know that went fast, guys. I know that went fast. It was like a fire hose, man, like a fire hose. But I figured with the videos, you'd be okay.
Awesome, thanks, Steve. Yeah, I'll share the recording with you guys on our platform, our teachers platform. Steve, your proof without words is actually how I got to know you and how I ended up searching for you on Twitter.
Oh my gosh.
I was showing my grade 8s the theorem of Pythagoras visually, and the thing I asked them to do was each of them should have their own proof without words. And
I think I remember that when you contacted me on Twitter for the first time. You were telling me about that story that you did with your grade 8s.
Yeah. So yeah, thanks. Yeah, thanks for that. So that's really cool, and that led me on a whole new journey. All the proofs that I currently do, I do with visual aids as far as possible. So yeah. Thanks for that, opening up a new world for me.
So guys, feel free to contact me at any time. I did not put my email. Let me put my email down here if you need something. I did not include it in the document. Let me put my email down here, and then I've got to run to. I've got meetings. It's the way it is.
Yes.
You know.
Interesting statue in the back.
So I just put that to Nadia. Sorry about that. Let me put that to everybody. So Phelps 31415@gmail.com. Feel free to email me at any time with any questions you have. I'll respond, or hit me up on Twitter. And I think we go again in 2 weeks, not next week, but the week after. Is that correct?
Yeah, correct.
All right. Awesome, guys.
Thanks, Steve.
Thanks for having me this morning.
It's a pleasure. Bye.
Bye, guys.
Voordat julle gaan, so ons het volgende week het ons 'n lekker reeks goedjies wat ons gaan doen. En dis vir alle onderwysers, is alhoewel die wiskundevereniging dit reël. 5 uit die 6 sessies is algemeen generies, en daar's baie mense wat vra as dit dieselfde as die wat ons voorheen gedoen het. Nee, dit is nie. Dit sal redelik nuut wees. Die enigste een wat spesifiek vir wiskunde mense is die GeoGebra een. En dan gaan Valentyn sy aanslag op GeoGebra wys, en dan bietjie meer in die konteks van Afrikaanse onderrig of Suid-Afrikaanse onderrig. So as jy nog nie 'n lid is nie van die VAW nie, en jy registreer vir daai sessies, ons gaan die eerste 250 registrasies, of ek dink 300 registrasies vir daai sessies, wat nog nie lidmaatskap is nie, het ons 'n borg gekry om voor te betaal. So ek dink dit is awesome. So as jy kan, maar dis uit die aard van saak slegs vir onderwysers. So nou nie vir ekstra klas persone of vir mamas en papas. Baie dankie julle. Ek hoop julle net so baie soos ek geleer. Ek het daai vryhand ding is vir my awesome. Ek love dit, want baie keer omdat jy vir kinders wys, hoekom is dit F+5, dan skuif hy links, en F-5, dan skuif hy regs, en daai is 'n baie oulike manier om dit te wys. So baie dankie. Julle kan julle dag geniet. Sien julle binnekort. Ek hoop julle gaan nou vir die 3 uur sessie, dis 'n baie oulike sessie. As julle kan registreer vir dit, doen dit, net bietjie om inspirasie inspuiting is sy naam. Lekker dag. Totsiens.